In the year 2022, astronomers employing the Murchison Wide Field Array made a noteworthy discovery. They detected an intriguing radio signal that exhibited a consistent recurrence every 22 minutes. These scientists were familiar with recurring signals, typically emanating from pulsars, highly dense neutron stars emitting intense light pulses as they rotate in the cosmos. However, upon scrutinizing historical observational records, they stumbled upon a surprising revelation. This signal had been reaching Earth since at least 1988, maintaining a remarkable degree of regularity that exceeded expectations for a rapidly spinning pulsar. If this signal indeed originated from a neutron star, it deviated significantly from any previously observed neutron stars. Consequently, the question arose, what was the source of this enigmatic signal? Today we embark on an exploration to uncover the mystery concealed behind this signal. A puzzle that holds the potential to challenge our understanding of some of the most awe-inspiring celestial entities in the universe. The source we are talking about, known as GPMJ 183910, is really far away from us, about 18,000 light-years. It sends out pulses of signals that can last anywhere from 30 seconds to 5 minutes. These pulses happen within a specific window of about 6.5 minutes, and they repeat every 22 minutes. At first, this might seem like it's changing a lot. The difference between 30 seconds and 5 minutes is big, and the timing of the pulses changing by more than 6 minutes doesn't seem very steady. But when it comes to neutron stars, things can get really complicated. If this source is indeed a neutron star, many factors can affect how long the pulses last and when they arrive. However, the scientists who study this carefully looked at data from the past 35 years. They used this big set of data to understand and reduce the variations. After doing some calculations, they figured out that this source spins around once every 21 minutes and 58 seconds, and they also measured how much it's slowing down. What surprised them was that this spinning speed had stayed the same for the past 35 years, even though they expected it to slow down as it gave off energy into space. We can say with confidence that if this source has been slowing down, its rotation speed hasn't changed by more than 0.28 milliseconds over the last 35 years. If it had changed more, we would have seen it in our data. This tiny change shows how incredibly steady this object is spinning, which is unusual for a slowly rotating pulsar. To understand why this is so unusual, we need to talk about pulsars and what makes them slow down over time. Pulsars are neutron stars, which are the leftover cores of really massive stars. They're incredibly dense, unlike planets like Earth, which have a lot of empty space between particles. Imagine a whole star made entirely of neutrons, with no electrons, protons, or empty spaces. Even a small amount of this material would weigh more than the entire global human population. A typical neutron star is about 35% more massive than our Sun, but squeezed into a sphere the size of Manhattan. That's incredibly dense. The reason they have such strong magnetic fields is still a mystery in astrophysics. Now let's connect this to the signals we see from pulsars. Where do these light waves come from? To understand that, we need to dive into the complex process that generates the signal. It starts when an electron near the pulsar's magnetic poles gets pushed by the magnetic field, creating a curved path of light along the magnetic field line. This marks the beginning of a pulse. The light moves in a straight line until its direction changes too much compared to the magnetic field, at which point it scatters and gives its energy to a field of electrons. This creates an electron-positron pair, each with their own momentum in a direction perpendicular to the magnetic field lines, and they release energy as synchrotron photons. These two special photons can make more pairs of electrons and positrons when they reach a certain angle compared to the magnetic field lines. This keeps happening over and over, making more and more photons in pairs until they don't have enough energy to make more. Then, these photons go out into space, while the original electron keeps making more curved photons and repeating this process along the magnetic field lines. This process is why pulsars give off such strong light, and we can see their signals from thousands of light-years away. But why do we see this light as pulses instead of a continuous beam? Well, it's because a pulsar's magnetic poles don't line up with its spinning axis, kind of like how Earth's magnetic North Pole is different from the geographic North Pole. So, pulsars are like giant lighthouses, sending beams of light into space as they spin. To us on Earth, these beams look like they're flashing on and off as the pulsar rotates. And that's what our telescopes pick up as pulses of light. What's interesting is that this light has really long wavelengths in the radio spectrum, so we need special radio telescopes to detect it. The light made by this process all has the same wavelength, and its peaks and troughs are all lined up. Also, the light waves are polarized, meaning they all line up in the same direction, which is a special characteristic of neutron stars, just like what we see in our 22-minute signal. Additionally, the signal sometimes changes for a short time, where the direction of the light's polarization suddenly shifts by 90 degrees and then goes back. This is another sign of what's happening at the poles of the pulsar. A lot of the data we've gathered suggests that the signal comes from a pulsar, which is a type of neutron star. Pulsars emit strong beams of energy into space as they spin, but they eventually slow down and stop producing these beams, entering what's known as the death valley for pulsars. We have a graph that shows neutron stars based on how fast they spin, horizontal line, and how much they're slowing down, vertical line. The death valley is like a gray band in the middle of the graph. Any pulsar below this line should have stopped working. Surprisingly, our signal is even below the lowest point of the death valley, which means if it's a pulsar, it should be completely inactive. But we're still detecting it. If we compare it to other known neutron stars on this graph, it's very different. Most neutron stars spin about 10 times a second to once a second. In contrast, our signal spins only once every 13-18 seconds, which is more than 1,000 times slower than a typical pulsar. This would make sense if it was rapidly slowing down, but it's not. This challenges our understanding of how we can still see it. So the astronomers who found this signal considered another possibility. Maybe it's a magnetar, which is a type of neutron star with an incredibly strong magnetic field, more than 10,000 times stronger than weaker neutron stars. Magnetars can have starquakes, where their outer layers shift due to their strong magnetic fields and slowing rotation. This can release energy in the form of detectable light on Earth. One famous starquake in 2004 was so powerful that if it happened within 10 light-years of Earth, it could have caused mass extinction. If anything could reignite a dead pulsar, it would be an event like this. However, for our signal, it seems we haven't solved the mystery yet. While starquakes like the 2004 one emit X-rays, no such X-rays can be detected from where our signal is, which is about 18,000 light-years away. Also, a magnetar's outburst, including the effects of a starquake, usually lasts only a few years at most. But our 22-minute signal has been going on for 35 years, which doesn't fit with the magnetar idea. So what else could this signal be? The astronomers have some other ideas. One is that it could be a white dwarf with an extremely strong magnetic field, but this would require a magnetic field stronger than any seen on a white dwarf before. Another possibility is that it could be low-frequency radio waves coming from interactions between stars and exoplanets, or binary systems of brown dwarfs circling each other. However, these emissions are typically much weaker than the 22-minute signal. In the end, none of these theories seem to fully explain the signal, but this is the kind of mystery that excites astrophysicists because it challenges what we know and could lead to new discoveries. The astronomers believe that there might be similar sources in the galactic plane hidden in the data they've already collected. Finding more of these signals could help us understand what's causing them. In the world of science, encountering mysteries like this drives curiosity and pushes us to uncover new things in the vast universe. What do you think could be causing the 22-minute signal? Let us know in the comments below.